So as I mentioned, my name is Esten Grøtli and I work at Sintef and I am located in Trondheim. So the outline of my talk will be as follows. I will start with increasing the level of autonomy in process industry and how AI and machine learning are important in that respect. There will be a non-technical definition of what AI and machine learning are, and I will introduce the basic machine learning paradigms. These are supervised learning, unsupervised learning, and reinforcement learning. Then we will look at some potential applications of recent advances of primarily deep learning for process industry, and I will reflect on the challenges related to uptake and implementation and give a overview for when we believe these methods are best suited. So this presentation is based on material from a project called Towards Autonomy in the Process Industry, TAPI, which I'm leading, and this is aimed at moving the Norwegian land-based process industry towards more autonomous operations by exploring the intersection between machine learning and more traditional model-based control methods. So I would like to take the opportunity to thank my colleagues for kindly letting me borrow some material from their presentations, and in particular Katrin Sel, who recently defended her trial lecture on this topic, and I have also used some slides from my colleagues Mark Herring and Ivan Bøhn, so thank you to them as well. And if this topic is of interest to you, then I will also like to take the opportunity to mention that the two PhD students in the project recently defended their thesis. So now Dr. Erlend Torjeberg Lundby, he defended his thesis on data-driven dynamical modeling in the face of data limitations just before the summer. And Dr. Katrin Sel defended her thesis on learning model predictive control just last month. But now, returning to why artificial intelligence and machine learning is important for the process industry. So as you logged on at 8 o'clock this morning to listen to this webinar, it might be like preaching to the choir, but anyway, process industry is about transforming bulk resources into other products. So this is obviously important to Norway, and I find this map, although from 2016, quite interesting, as it also illustrates how important process industry is across most of Norway, perhaps with some exception to Finnmark and Innlandet. So returning to the project that I've been leading towards autonomy in the process industry, why should the process industry aim at an increased level of autonomy? Well, it could help removing people from high heat, acidic, dusty, or otherwise dangerous areas. It could increase sustainability. It has probably never been so much focus on reducing energy consumption and pollution. And finally, we might want to increase the levels of autonomy to be competitive, to be able to sell our products on the European or global market. So one way to achieve this could be through better knowledge of the process, which can be achieved by better models. And this is where AI and ML comes into play. So modeling is important, and here we're talking about modeling of a physical process that's transforming bulk into other products. And we're not, for instance, talking about a business model or organizational process, although this can be equally important. So this can, for instance, be useful in state estimation, knowing more about the process than what you would do from measurements alone. And this, again, can be used for making the right decisions by the operator. And finally, it can be important for the design of controllers where knowledge of the process is used to take safe and possibly optimal actions. However, many of the processes that the industry partners are faced with are not trivial to model. They can, for instance, be characterized by having complex nonlinear dynamics, time delays, meaning that there might be a long time from imposing an action until you see the effect of the action. And without a structured approach to testing, it might be very difficult to see which action caused which effect. Then many of these processes appear under very harsh circumstances. So think, for instance, of processes with high temperature or being very acidic. So sensors might not withstand these conditions, and it becomes very difficult to measure the wanted states directly. So instead, you have to measure related features or states, for instance, through remote sensing. And if this harsh environment prevents continuous measurements of the process, then you will perhaps have to do manual sampling, and this can often be irregular or make the process undersampled, which makes it extra difficult to identify the underlying dynamics. So TAPI has aimed at investigating what is possible to do in the intersection between physics-based and data-driven modeling, despite these challenges. And an important part of this is, of course, data-driven modeling and, of course, machine learning. So this brings us to the second part of this talk, which is a very brief introduction to what artificial intelligence and machine learning is. Sorry, that was the wrong slide. So artificial intelligence can be defined as the ability of machines to perform tasks that are typically associated with human intelligence, such as learning and problem solving. Unfortunately, I would say that this term has maybe lost a bit of its original meaning, and today it can mean pretty much anything. And this is something to be aware of. Someone might have a very specific idea what AI is, while others use it in an incredibly broad meaning. So personally, I feel that machine learning is not as misused, and it simply refers to the methods where computers learn from experience. And machine learning has seen a surge in attention recently. And this is due to increased amounts of data. All the devices that we're carrying with us are collecting data. All the cars have more sensors and so on. There are powerful and cheap computational resources available for training and for data gathering. And there has been advances in algorithms and methodologies to recent years that have been able to take advantage of these improvements in computations. Now, as I mentioned, there are three basic machine learning paradigms: supervised learning, unsupervised learning, and reinforcement learning. So in supervised learning, you have labeled data. That could be a data point x1, which corresponds to a data point y1, and x2 that corresponds to y2, and so on. And with all these corresponding data points, you can learn a mapping from the input x to the output y. So in this case, you learn the mapping f. And in the simplest case, this could be a linear mapping, just a straight line going through this point. And supervised learning is often used for regression and classification problems. Unsupervised learning, on the other hand, is a technique that learns patterns or groupings from unlabeled data. And this is very useful for clustering and dimensionality reduction. The third paradigm is reinforcement learning. And this is a technique for finding policies that maximize some reward. So the policy is updated by interacting with the environment. So you look at how a certain action affects state of the environment, and then this gives you some reward. So reinforcement learning is, for instance, much used for board and computer games, where it is non-critical to if you're picking the wrong action. So Actually, I don't know if you can see this video, if it's playing. So this is just an example of reinforcement learning. So it's also been very popular within robotics. So this shows an example of how you can learn a robot to walk. So in this case, the agent would be the robot. The policy would be how to move the legs. The environment is the robot dynamics and its surroundings, and the reward is the walking distance. So now that we have the three paradigms in place, I would also like to mention another term, which I think is important to know. It's artificial neural networks. So artificial neural networks is based on a collection of connected units or nodes called artificial neurons, and these are loosely based on neurons that you find in our brain. And these artificial neurons, they receive signals, then process them, and send them to neurons that are connected to it. And these connections are called edges. And these neurons and edges typically have weights that are adjusted during learning, depending on the strength of the signal of the connection. So on the left here, you see a figure of a neural network with some input layer in green, some intermediate layers in blue, and output layer in red. And deep learning refers to having multiple of these hidden layers. I would also like to mention that neural networks are universal function approximator, which means that under certain technical assumption, a neural network can approximate any function to a desired given accuracy, given enough data. Now, finally, one last term I would like to mention is generative artificial intelligence. This is artificial intelligence that is capable of generating text, images, code, etc. And there's been a lot of buzz around this lately, especially with the release of ChatGPT. I think it was last November. And you can also see this image to the right of, I believe it's from Dali, where he's been, where the Pope has, or an image of the Pope has been generated, looking more like a gangster. So that, I think, concludes this part of the presentation. I will not go too much into these generative artificial intelligence and ChatGPT, but I think that the next presentation in this series will be about ChatGPT. So I think you should tune into that if that is of your interest. Now, let's look at some applications of these recent advances. So the few applications that I selected are soft sensing, so doing time series prediction. The other is process monitoring, doing anomaly detection. And the third is advanced process control. So there could probably have been a lot more applications of how to use this deep learning, but these are a selected few. And I think also these examples fit quite well into the different paradigms that we talked about. So the perhaps obvious first thing to start with when applying machine learning to a process is to try to learn a model that can predict some time into the future. And this might be useful for online prediction of process quality, which are otherwise difficult or costly to measure. There might be long delays causing this, but if you have this time series prediction, you can, for instance, give the operator information about the process quality online, and he relax, or you could give him or her the possibility to act early on, for instance, a predicted reduction in quality. So this is why this is important. So an example here could be a multi-step ahead prediction of catalyst activity in the methanol process. So there's a paper there by Ali Beatty from 2020, where they have trained a multi-step ahead prediction using a recurrent neural network, which is a type of neural network model designed for sequential data such as time series. And they train this to predict this into the future, and then this allows the operator to act according to these predictions. The second application that I wanted to mention is on anomaly detection using autoencoders. So first of all, anomaly detection is about detecting changes from an established normal condition. So detecting these changes might be important in order to schedule maintenance of a faulty component, or to adjust or stop an operation before something seriously goes wrong. So the red circles in the figures might be what we, at least humans, classified as anomalies. They appear to be something that is different from normal conditions. So one way to detect anomalies could be by autoencoders, and this is what's been used in the reference on the right for fault detection in a chemical process. So autoencoders are neural networks that are trained to map the input sequence to a latent space or latent variables. And then a second neural network is trained to map from the latent space back into the input space. Now, when this autoencoder is trained and it sees some normal data, it will give a low reconstruction loss. On the other hand, if there's something unusual, such as an anomaly, then it will give a high reconstruction loss. So the steps of applying an anomaly detection with an autoencoder can be summarized as follows. First, you train the autoencoder on the normal operation data. Then you define some threshold for detecting the anomaly. And this threshold is defined depending on the reconstruction loss. So if the reconstruction loss is greater than the threshold, then there is an anomaly, and otherwise there's not an anomaly. And we'll say that this method has also been tested in a use case in our project. So in this case, Hydro has kindly let us work on some of their data. So here's sensors are inside a ventilation channel. And there's a certain temperature and pressure inside it. But unfortunately, there's also some particles that causes growth on the sensors. So this might be some measurements or readings that you get, but looking at the temperature readings, when you get a growth on the sensor, there is an increased variance due to this growth, and you cannot really trust the sensor readings. So therefore, you want to detect this as soon as possible, so you can do the correct measures to account for this and clean the sensors. But at the same time, you need to ignore jumps and other things which are considered normal operation modes. Then I will move on to the last example, which is on advanced process control. So there are many impressive results on using deep reinforcement learning including the work by Kaufman and co-authors in the video on the right, where deep reinforcement learning was used on drones to make them better at drone racing than professionals or even champions. But despite this impressive result, reinforcement learning typically require online interaction with our system, and it's often based on trial and error. And this is not good for safety critical systems that you typically have in the industry. So therefore, I haven't found any real good examples of applications of reinforcement learning yet in the process industry. If anyone has some good example, I would very much like to hear about them. Some of the methods, however, that are being explored to deal with this is doing training for simulation. This makes it safe, although the drawback is that first of all, you will need a good simulator, and there's still often the problem of taking the controller from the real world to, from the simulated world to the real world. And this is often called the simulation to reality gap. Others have looked at safety filters. So this is a method where exploration of this reinforcement learning agent is constrained in such a way that you know that you can find your way back into a safe set with a nominal controller. The third avenue that typically being explored is offline exploitation of existing data sets. So you can imagine if you have a number of factories that are similar, and you can collect data from all of this, or in a safe manner, then maybe you can also apply it to factory N+1 that have some similar properties. So these were the three examples that I wanted to mention. Now to give some reflections of what we have seen in the literature and the potential applications. We see that there's a gap between what is currently being published in research and what is applied in the process industry. So obviously there's some time from a new method is published until it's implemented in an industrial setting. But aside from that, reasons for these methods not being applied already could be that deep learning models are generally data hungry and difficult to train. So simpler models might be just as good, or actually the only ones that are possible to use with a small amount of data. Then there's a point of quality versus quantity. Even if you have a lot of data, all this data might not be useful for training. You can, for instance, have some sensors that are making the same readings over and over again because the operation is sort of in a steady state. Then you cannot take advantage of all these data points. And this is sort of similar to the next point I'm mentioning. A lot of the data could be from a closed loop operation. So the process is at steady state and you get the same data points most of the time. And I should also mention that if you're mainly operating very close to some equilibrium point or equilibrium state, then simple models will typically do, as you can approximate the states around this equilibrium pretty well with simpler models. A third point I would raise is that deep learning models are black boxes. There's a lot of research going into this to build explainability around deep learning models. But for now, they're sort of black boxes, and for an operator, understanding why a model does what it does is really important. So it's not that easy to roll it out into industrial setting. Then finally, processes might change over time. So these require retraining, and this might be very time consuming. So in fact, I thought I will also show this. What are the main benefits and shortcomings to neural networks versus more simpler models? Let's call them linear models. So neural networks are slow at training. They're difficult for checking data requirements, and they're difficult to use in control, I would say. They're good for predicting both short and long time horizon, and also for monitoring in this respect, and they're well suited for classification. Analyzing resulting models is, on the other hand, difficult, and model reduction can also be difficult. And yes, also the size of the required data set, as I mentioned, needs to be large, which is a drawback. Yes, then the model validity is usually bigger with these deep learning models, but you need a large number of, or this model contains a large number of parameters, which you need to train. Then for what applications should you use neural networks? And when should you use these linear models? We believe that for most control applications of today, you should still use linear models. If you're modeling a furnace where all important environmental influences are measured, you should probably use a neural network. But if some of these important influences are not measured, then you should probably stick with a linear model. Neural networks might be very good for anomaly detection, as we saw. And they could be good for modeling slow variations in the frictions of a wall due to wear. If you have a data set of a very limited number of measurements, you should definitely use a linear model. And we also believe that if you have a chemical process with several 10,000s of inputs and outputs, then a neural network will just become too large for training, and you should still use a linear model, unless you're someone like Google and have very big amounts of resources available. Then perhaps neural network could also work. Some more reflections. There seem to be a gap, as I said, between research and what is applied in the process industry. So despite simpler models might be as useful as deep learning models, there's also some practical bottlenecks related to data management. For instance, who should have the data? Do you need to bring the data outside the firewall to do training? Probably not. To apply these methods, you need the expertise in-house, which obviously also takes some time to build up. And then there's the testing. How can you test these methods in a safe manner? Then there's the conservatism. If you have something that's working well, then you might not have the push to put the required resources into applying new methods. Furthermore, it's time consuming to roll out. And also, I should mention that what we find in the literature might not be representative for what is actually happening. So there might be some competitive considerations that someone that have applied reinforcement learning with great success don't want to mention this to the competitors, and they don't want to publish these results. So this brings me to the summary of my presentation. We looked at artificial intelligence and machine learning, and how methods from AI and ML has been proposed to increase the level of autonomy in process industries. I've given a brief introduction into AI and machine learning terminology, and we look at some application of this, and where I believe the speed of the uptake is determined by the purpose. So The first step is probably within sort of decision support, anomaly detection, and time series prediction is something that's easy to roll out, whereas control applications probably take some more time. Then we looked at the challenges of applying neural networks, and I've given some overview of when we believe neural networks should be applied and when you should apply simpler models. So thank you. That's what I had planned to present, and then I guess I'd take some questions if there's any.
Thank you so much, Esten. This was a fantastic presentation. I liked it a lot. I hope that everyone else do as well. If I could start with one question, I would like to say the link between analyzing and sensors are, of course, the quality of the sensors data that you provide. The focus on edge computing has become more and more essential as we go along, and that's been focused on the quality of what you put into the analyze. What is your perspective about that? Because back in time, there was always the focus that the bigger data you could provide, the better, and everything was essential, but the quality is now more in focus, isn't it?
Yeah, I would say so. I think I think at some point everyone was thinking that if we just had enough data, we could do anything, and data was gold. And maybe in some sense it still is, but I think it depends highly on the data, as you say. So a lot of the data that we see are just repeated measurements. It's you're doing the same measurements of over and over again, and especially for dynamical systems, which is the core interest of me, where you have some temporal and perhaps also some spatial changes, then doing the same measurement again and again doesn't make you able to identify any dynamical system. So I think a lot of the data is not as valuable as perhaps we thought some years ago.
Good answer. I also have a question from the audience. Adelun, could you tell us about your question, please?
Yeah, hello. My name is Erland. I work for Elcam, and one of it's actually so my question is somewhat similar to the previous one, but it is what is the quality, because what is difficult is for us is to know what quality do you need in your data to apply a neural network. Like what type of resolution do you need? What's the statistical resolution? What type? Like is it sensor data? How our data will be poisoned because of operations? That's just what happens. Like what degree can you have? That sort of thing.
Thank you. It's a very good question, and it's something we've tried to answer in TAPI, and I think unfortunately it's not a general answer to that. The requirement that you have to the data is always related to the model that you try to apply. So if you try to apply a simple model, there's going to be typically less requirements to the data. And if you try with a neural network, then it also depends on how many layers will you use, how many parameters are in your model. So there's not a single answer to this, I believe, but the requirements will depend on the model that you've chosen and that you'll try to train.
Yeah, is there some sort of mathematical test? Because when you run like general fitting models, you can do statistical model validation. Is there something similar for the AI systems so that we could run internally to check before we go and ask Sintef to do something for us?
Ooh, that's a very good question. I think I will have to forward that question to some of my colleagues to actually come up with a good answer to that. Yeah, I'm sorry, I don't really have a good answer to that. This exists.
There is also others that would like to have a question here, so I hope it's accepted that I go further. But I would also mention one thing: uncertainties. To know the uncertainties of the sensors, I think, are vital. Not only the uncertainties as you start to do the measurement, also the changes over time due to the environment. That if you know that, you know at least where you set your limit of your precisionness in your calculation thereafter. Sorry, Håkon Måløy.
Hello.
Hello.
I have a question related to the types of neural networks you applied. Did you find any relation between types of neural networks like transformers or LSTMs or graph neural networks, and find that any of these models compare favorably in these applications?
Yeah. I would say for time series prediction, so LSTM are typically the ones being used there. This is because you sort of need to have some memory in the process when you're trying to learn a dynamical model. So that's definitely a answer to that. I know also for the reference I mentioned when dealing with autoencoders, that they also used LSTM steer. To say which type of neural network is best for a certain application, I'm not sure. Again, I think that's maybe some of my colleagues would be better at answering that. So I could perhaps get your question and forward it to one of them and come back to you with a good answer. Yes.
Thank you.
So I think if there's no more questions, we are close to run this off. Thank again to Esten. That was fantastic, and we hope that you also will attend the next breakfast webinar. Will be in next month, and that is KI-assisted programmering for data analysis, which is somewhat in the same theme as we have today, but it's more on machine learning and ChatGPT. So I hope that you also will attend that one. So thank you again, Esten, and I hope you enjoy this presentation. Thank you.
Thank you very much.